I've got one more problem up here on the board. This is very similar to example 3 in your text. I've just switched the roles of x and y, but I think it's an important example to look at. It's a pretty tough one. Okay. So we're in 2 space approaching the origin, okay, but I can't plug in 0, 0 because the bottom would go to 0 and so would the top. Does not look like any substitution would be helpful because I see different expressions on top and on bottom. We are approaching the origin in 2 space, so I'm going to try switching to polar coordinates. I'm a little bit skeptical about that just because I can see that I'm going to be getting some sines and cosines then in the denominator that aren't going to cancel. And while sine and cosine are bounded, their reciprocals are not. So let's try it. If it works, great. If it doesn't work, we'll sort of see one of the limitations of times when we should maybe be a little skeptical. Okay, so I'm going to switch to polar, with r being the square root of x squared plus y squared. So then this is the limit as r goes to 0 from the right. It's a one-sided limit. X squared times y. X squared is r squared cosine squared theta. Y is r sine theta. And I'm actually going to just combine that r with the 2 that I already have. So we have a total of 3 factors of r, and then 2 factors of cosine and 1 of sine. In the denominator, x is r cosine theta, so x to the 4th is r to the 4th cosine to the 4th theta. Y squared is r squared sine squared theta. Now in the denominator, I can factor out an r squared. So we'll have the limit as r goes to 0 from the positive side of r cubed cosine squared theta sine theta over r squared times cosine to the 4th theta plus r squared sine squared theta. So I can cancel 2 factors of r, and that does leave me with an r left over on top. So we'll have the limit as r goes to 0 from the positive side. I'm going to just factor out that r, and then the fraction that's left is cosine squared theta sine theta over cosine to the 4th theta plus r squared sine squared theta. So I can see this factor is going to 0. The limit will be 0 if this factor is bounded, and I don't think it is. Okay. Because I can see that I can make the denominator get arbitrarily close to 0. This term is going to be going to 0 because r is going to 0 and sine squared is bounded. But cosine to the 4th could get arbitrarily small. And while I've got a cosine squared on top, I can't cancel across this addition, but if I say, that's negligible, even if, I completely ignored that term, I'd still have more cosines on bottom than I would on top. So this looks to me like it's unbounded. Okay. Now, I do just want to mention, it's not the end of the world to have sines and cosines in the denominator. If I didn't have that r squared there, if the denominator was just cosine to the 4th theta plus sine squared theta, okay, that's something that is always positive, okay, because it's 2 even powers of things, and those 2 things are never simultaneously 0. So one of the terms could be 0, but they can't both be 0. So that's always positive, and that would have a smallest value and a biggest value that it could take on. So if I have sines and cosines, and they're both positive, or the same sign, both negative would work too, then I might end up still getting a fraction that was bounded. If one of these was an odd power, then I'd have something that's sometimes negative, sometimes positive, so it's going to be 0 somewhere in the middle, and if the denominator can get arbitrarily close to 0, my fraction's going to be unbounded. Okay. All right, so I'm thinking this isn't working. Now, I can't conclude here that the limit doesn't exist, because essentially what I have is one factor going to 0 and one factor where I'm not sure what happens. I think the limit of this piece doesn't exist, but sometimes when you take something where the limit doesn't exist and you multiply it by something where the limit does exist, you get a finite limit. So I'm highly suspicious here that the limit doesn't exist, But I'd need to do some more investigation, and I don't feel like working with two variables like this. Okay, so switching to polar wasn't particularly helpful, although it made us suspicious that the limit didn't exist. So I'm going to try paths. Now, if we're approaching the origin, that's right here, the simplest paths that go through the origin would simply be the vertical and horizontal lines, which would be the two axes. Okay. So let's just let R1 of t be t0. So that's the x-axis. Okay. So then we'd be taking a look at the limit as xy goes to 0, 0 along R1 of t of x squared y over x to the fourth plus y squared. Okay. And that would be the limit as t approaches 0. That would be the value t has to get close to for this to go to the origin. And now we're replacing our y's with zeros. So on top, I'm going to get 0 because I'm getting 0 times t squared. On bottom, I'm getting t to the fourth plus 0. Okay. Well, if I have literally 0 on top and not literally 0 on the bottom, that limit is 0. We've seen this before. This function of t is undefined at 0, but everywhere else I've got 0 over a non-zero number. That's going to give me 0. So the limit is 0. Excellent. So now let's try path 2. Let's try R2 of t as the y-axis. Okay. And then we'll take the limit as xy approaches the origin along R2 of t of x squared y over x to the fourth plus y squared. Okay. So xy is here. I'm still writing it in terms of xy. Now let's switch to t's. So this will be the limit as t approaches. It'll be going to 0 again. And this time, we are replacing the x's with 0. So we're going to get 0 times y is 0. And then we're going to get 0 plus t squared. But we literally have 0 on top. That limit is 0. So we got the same thing. Okay, rats. We're going to have to look at a third path. Okay, so I'm going to just choose the line y equals x. So let's try that. R3 of t, that would be t. Okay, that also goes through the origin. Do make sure your path goes through the origin. Okay, let's see. So limit xy goes to 0, 0 along R3 of t of x squared y over x to the fourth plus y squared. That's going to become the limit as t goes to 0 of t cubed, because I'm replacing both x and y with t now, over t to the fourth plus t squared. Okay, so that's the limit as t goes to 0, t cubed over, I can factor out a t squared, and that's times t squared plus 1. I can cancel two t's, so we get the limit as t approaches 0 of t over t squared plus 1. Now at this point, I can plug in 0, and I get 0. Okay, so we've tried 3 different paths. We got the same number. Okay. Now, if I'd started with paths, this might make me say, you know what, now I'm suspicious that maybe the limit exists and that it's 0, and maybe I'll try another technique. And if I hadn't already tried it, I might try switching to polar coordinates. But my work in polar coordinates made me suspicious that this limit didn't exist. Okay. Now, I've been trying simple paths. I've been trying lines, because that's strategic laziness. You go with a very simple path. And very often, that's enough to show that a limit doesn't exist. But not all paths are straight lines. In fact, in example 3 in the book, which is very similar to this, they just have the x's and y's switched around, they actually demonstrate that along any straight line through the origin, you will get the same limit of 0. Okay, so we're gonna need to try a path that's not curved. So if this happens to you, if you keep getting the same limit, you haven't proved anything, okay, you might say, I question my initial judgment that the limit doesn't exist. Let me see if there was a technique for proving that the limit existed that might work. Or you might say, I'm not choosing creative enough paths. Okay. So I'm going to try a curved path. All power functions go through the origin. So I'm going to try R4 of t to be t squared. That's just y equals x squared. That's my beautiful parabola, and that goes through the origin as well. Let's take a look at what happens there. If I look at the limit as xy goes to 0, 0, along R4 of t, x squared y over x to the fourth plus y squared. That's going to become the limit as t goes to 0. Now I'm replacing x with t, and I'm replacing y with t squared. So x squared becomes t squared, y becomes t squared. Okay. X to the fourth becomes t to the fourth, plus y squared becomes t squared squared. That's going to be the limit as t goes to 0. This is t to the fourth. That's t to the fourth plus another t to the fourth. This is very exciting. This is the limit as t goes to 0 of t to the fourth over 2t to the fourth. I can cancel those t to the fourths, and I get 1/2. And now I make the brilliant observation that 1/2 does not equal 0, and so the limit as xy approaches the origin of x squared y over x to the fourth plus y squared does not exist. Okay. So we needed to try a curved path. Want to just talk about strategizing about how to find something here. Okay. Everything that I had involved just powers of x's and y's. And if I was writing things as powers of t, I could see that if I was getting t's left over on top, we were going to be getting 0. Okay. So what I wanted to do was not have t's left over on top. Now here, when I just plugged in t for x and y, I could only factor out a t squared. Okay. But I got 3 factors of t there. So I wanted to somehow make the power of this term bigger. So by having y being t squared, this power became bigger so that I could combine them. They ended up both being t to the fourths. And then I had 4 factors of t on the bottom, wasn't limited to just factoring out 2 of them. I mentioned in the textbook, they have this same problem, but with the x's and y's reversed. The path that they used was x equals y squared. Okay, so if you need to go to a curved path, you may want to spend a little bit of time strategizing about why do I keep getting 0? Oh, I keep getting 0 because I end up, since these pieces are connected by multiplication, if I've got powers of t, those powers of t just combine, whereas here I can only factor out the smallest power of t. So we wanted to somehow make this power a little bit bigger so that we could factor out something bigger on bottom so that we didn't have t's just left over on the top. Okay. So a little bit of strategizing. This was definitely a tough problem, okay? But I wanted you to see it, and now you've seen it here, and you've also seen it in the textbook. If you look at example 3, very similar problem. If you have something like this, keep in mind the lessons that we've learned, but you're showing your work. There's plenty, let's say we didn't get to this last path, but you tried converting to polar coordinates, and you said, oh, this is indeterminate, I'm not sure what's happening, and then you tried paths, and you tried those paths. Lots of opportunities for partial credit. So I definitely would love to see everybody be able to get to the final answer, but don't despair if you've got something like this, and you do get stuck. There are lots of opportunities for partial credit on a question like this.